Hello everyone, welcome back. We're looking at the importance of interpreting graphs. Now, there are lots of ways that an examiner or a teacher can ask questions about graphs. Can ask questions about comparing graphs, all sorts of things where you can have to read off values and predict what's happening and make some deductions. But I thought that I would separate out some special features of graphs for us to look at, which will help our understanding not just of the relationships that the graphs tell us about, but how we can see what's happening as certain things change. So the first thing that I want us to look at is when you look at a graph, look and see what the maximum and minimum values are. Now, this isn't something that happens on every graph, but it is useful to see where the graph starts from and where it ends. The most important type of graph that we look at is particularly the linear graph, the straight line. And ask ourselves, does it start at the origin? Because you already know that if it starts at the origin, then it could possibly be directly proportional. And particularly if it's a straight line, then we know that it will be directly proportional. But it's not only where it starts from. So this one, we're looking at starting just on that side, but we're looking at the maximum value as well. And the maximum value over here is somewhere in that region there. I haven't put values on this axis, but I just wanted to show you that there's an important feature that happens when we get a curve like this. This is the graph showing the distance a ball travels when it's thrown up. So the ball starts on the ground next to where I am, and I'm going to throw it up into the air, and we're going to see how far it gets away from me and what's going to happen as it comes back down again. So it's about the distance that it's traveled, and what we can see, it's a kind of the distance above the ground. So this is the maximum height. And what I think is very important here is to recognize that initially, that when we look at this graph, we'll see that in one block of time, look, it's traveling more than 2 blocks of distance. And if we look at the next section for the next block of time, there's another block of time there, look how far it goes. It's not even going 2, it's going 1 and a bit. So what is this saying to you? It's traveling less and less in equal intervals. So it's often good to look at time intervals and say, what's the change within each time interval? And so if it's going less and less, what does that mean? It tells us that by looking at this, it is slowing down. Have a look if I'm correct. Take this time interval. Now it's the same time interval that we went more than 2 blocks. We'll start at this point and we'll end at that point. Can you see it hasn't even got a height or a distance traveled of 1 big block. It's a little section so it's going very, very slowly. It's getting slower and slower. So the other way to look at this is to say what's happening to the gradient of a line that is just touching the curve at one point. And I hope you can see, I'll just use my finger here or my hand. Over here it's quite steep. Over here it's less steep. Over here it's less steep. Over here it's less steep. And over here it is horizontal. In other words, at that point it's stopped moving. Just for a small interval of time, it's got to 0 velocity. So what I'm showing you on this graph is that the maximum value is at the highest point above the ground, and at that point, the stone has, or the ball, what was it? A ball travels up. It has stopped moving upwards. It has got 0 velocity, and it's now changing direction and starting to move down. And that change in direction is very important because velocity is a vector quantity. So if we recognize something over here, you'll recognize when I put my hand like this, that line that is drawn as a tangent to this curve has got a positive gradient. But on this side, the gradient is negative. And notice over there it's flat, over there it's a bit steeper, and over here it's getting steeper still, and over there it's steeper. So it's getting bigger and bigger in the negative direction. And that means because it was going up was positive and down was negative, we have to recognize that as a vector quantity, there's been a change in direction. And so I hope you can see graphs give us a lot of information and tell us a story of what's happening to this ball that we threw up in the air. And from this graph, we could draw a secondary graph, which shows us that there's been a change in direction. So I'm going to draw a sketch graph over here just to link the two together. And the sketch graph that I'm going to draw is the sketch graph of the velocity versus the time. And if you notice, I started with a big velocity that was positive, and it decreased until 0, and then it's increased as it's gone further and further down. That's not very accurate. It should have been the same. It should have been symmetrical, but it gives you the idea. Whenever it crosses the axis, this time axis, that was the positive velocity. This is a negative velocity. It's changed direction. This point here, that point there, correlates to the highest point. So at the highest point, the stone has 0 velocity, but it has the maximum height above the ground. Okay, so I hope you can see there's lots to tell by just looking at key features like minimum points and maximum points. The other thing that is important as a feature of a graph is where there are horizontal lines. Where the object or the curve of the line flattens off and it becomes horizontal. Now, this is telling us something very important. So have a look at the example and we'll see exactly what's happening. So here I've misspelt. This was the volume measured in centimeters cubed. And we're just going to correct that. This is the time over which that happens. So if we've got a chemical reaction that's, for example, producing carbon dioxide, we could collect those bubbles of gas and measure the number of the volume against time. And so what do you see? Similar to in the first time interval, lots of bubbles. In the second time interval, okay, you can see here it was 2 and a bit. In the second time interval, it's just 1 and a bit. And in the third time interval, it's also 1 and a bit. So this section here seems to be fairly constant. And so we could say that is more or less a straight line. And we could measure that and call it the rate of the reaction, or the rate, the amount of gas collected per unit time. And it's happening at the same rate. But notice what's happening over here. It's slowing down. And even over there, it's slowing down. And over here, it's stopped. There's no increase or decrease in the volume of gas. So what's happened? The horizontal bit to the line tells us that this reaction has ended. The reaction has ended. And there's now a constant volume that's not changing. And we can read off the final volume of the gas that we've collected. So again, it's very important. Remember the shape, remember the minimum point, the maximum point, the steepness, and the change of the steepness over time, and when it becomes horizontal. Horizontal is telling you something. In this case, it tells you that the reaction is over. Now, let's look at another feature that we might need to focus on. We've said something about it already, and that's about crossing the horizontal axis. This is particularly important when we're dealing with vector quantities, because remember what a vector quantity is. It's something that has magnitude and direction. And we can indicate that direction as being, for example, positive or negative. So in the graph, when a value crosses the horizontal axis, then there's been a change in direction. So have a look at this graph. We've seen one like this before. What's it telling us? Because we've got a number of features. Notice this one is telling us that this is increasing velocity. So the velocity originally was 0, and it's getting, in time, it's getting more and more and more. But notice that these are the same sort of increases. So it's a constant increase. So it's not just getting faster and faster, it's getting faster and faster by the same amount. That's what this straight line indicates. Very important to see that. But now what is this saying? The velocity now, it's gone to horizontal. Is that saying it's over, that it's stopped? No. What it's telling us, that it has a constant velocity. So if this was 20, as an example, at that time, it's still 20 at that time, it's still 20 at that time, still 20 at that time. It's just not getting faster. It's not slowing down, and it's not speeding up. It has become constant. So just like the volume became constant, this illustrates the constant velocity. Now, what happens if we get a negative gradient? Well, what's happening to the velocity? Over here it was 20, over here it's got less, and it's now increasing in the negative direction. So as we go down here, we can say it's slowing down. But over here, it's speeding up. And what's the difference? It's crossed the axis. So it's gone forward, slowing down, turned around and moved back in the opposite direction. So it's very important to see that. Slowed down, got to 0, moved in the opposite direction to what it originally was. So it's kind of reversing. And that's what happens when we cross the axis. Okay, guys, I hope this has helped us to look at graphs, to sketch them, to draw them accurately, to extract information from them, and also to interpret the features of the graphs so we can have a link between the graphs and the relationships that we're investigating. It's been a lot of fun being with you today, and so I'm going to say goodbye, and we'll see you again soon.